It's a new chapter. So we go into the circuits and currents. Okay, we look at a circuit, or connect the resistors with batteries and see what happens. Electric circuit. So we'll start with sources of EMF. That mean batteries. EMF stand for electromotive force. That is, any device that sends current through a circuit. We call it as EMF. That is a battery or EMF source. Second topic is we will have resistors in a circuit, such circuits. We will connect them in series and see what happens, connect them in parallel and see what happens. Like we did for capacitors, remember in the previous chapter, we did this with capacitors, connected them in series, connected them in parallel, and tried to get the equivalent values. So we do a similar thing with resistors. Then when the circuit becomes complex, we cannot, do this equivalent resistors, which become a bit difficult. We cannot reduce all the resistors to one resistor, so we won't be just use the Ohm's law to solve problems. So this guy Kirchhoff, he came up with some rules, two rules actually, and we will use that to solve, analyze complex DC circuit. In number 5, we'll bring those two, resistor and capacitor, in a circuit. So that's why I call it RC circuit. R stand for resistors and C stand for capacitors, and connect to battery and see what happens. These two sections are omitted, so we will not work on it. So quite a short one, but we have to practice solving problems, electric circuits. It is interesting, not difficult. We will manage. Right. So what is an electric circuit? Even if you take a battery and connect it to a resistor, there we go. We have a circuit. Circuit mean, a closed path. So this is a loop. Okay, it's a closed path. We take pieces of wire, connect it to one side of the battery, other wire to the other side of the battery, then go and connect to the resistor. We got a very simple circuit. The electric circuits control the flow of electricity, that is current, and the energy associated with it. Circuits are used in many applications. So any electronic thing, like your mobile, they have circuits, electronics. So it's in many applications. Kirchhoff's rules we will use to simplify the analysis of simple circuits. Some circuits will be in steady state, meaning the current will be a constant current. Okay, it does not change with time. So the currents are constant in magnitude and direction. It will be flowing in the same direction. It will not reverse its direction. Circuits containing resistors and capacitors. If you have the capacitor, what happens? You don't have steady state. You will have sometimes transient current, stay there for a short time. It varies with time. Okay, sources of EMF. What are sources of EMF? I told you EMF stand for electromotive force, something that drives the current through the circuit. Electromotive force. Just make the electrons to move. So it can be done by a battery, a source of energy. So sources of EMF are batteries, generators, those are the sources of EMF. And the EMF of a battery is measured in volts. It's simply, you have seen this 1.5 volt battery, right? If you measure the potential difference, that is EMF of the battery. So what is the EMF? The potential difference that is created between the two terminals of the battery, that is the EMF. We use the symbol this, epsilon for the EMF. And of course, it is the unit will be volt. It's a potential difference. We already knew that potential difference unit is volt. So here we have the simplest circuit that we can imagine, a battery, like probably the 12 volts of the car, and connected to a resistor. A resistor will look something like this. If you draw a schematic diagram, you will be having symbol for the battery. The long side is the negative positive, so let me use the same direction. So short side is negative, and the resistor will be shown like this. That's it. So this is how you draw a circuit with the symbols. Yeah. Yeah.
When I want to like charge the landing, there is like this
battery resistor. Oh yeah.
So without this
resistor can control the amount of current. So we need to do that. Very small, but the resistance can be big, small. Size may be very small, but we can have a big resistance in a small like that. Okay. The circuit, any electrical appliances will have circuit connecting the elements to one to another. Always there will be resistance, not just one, there will be plenty of resistors. So where we use it, almost any circuit will have resistors. So your phone, okay, any electric device will have not one, plenty, many resistors. Each resistor will have a certain value, and each value has a specific purpose. So where will you use it? Everywhere. Everywhere, basically everywhere. You don't see it. It's because if you take the phone, there will be electronic circuits inside, but they are so miniature, small, very small. So everything has a resistor. There will be diode, there will be transistors, so many millions of components in it. It's like a computer. It's got. So I cannot simply answer your question. Where do we use it? I can only say everywhere. Okay, everywhere. Right. You will learn if you are in electrical engineering. You will learn more about it. But I cannot put everything now. Okay. So this battery, now we are talking about the battery. This battery, now you will think, okay, this is the only resistor, right? But when the current flows through the battery, so it is going like that, the current will be going through the battery as well. So there will be a resistance to motion of the charges even inside the battery. So effectively, it is like having another resistance inside. So we call that the internal resistance of the battery. We don't want it, but we have no choice. Any battery will have its own resistance. We call it internal resistance. An ideal battery should not have any internal resistance, should be zero. But practically all the batteries will have internal resistance. So it is there, we cannot help it. Then what happens, you may say this battery EMF is 12 volt, right? But if you take a voltmeter, okay, let me take a voltmeter and check when it is connected to this resistor, check the voltage, you will measure it to be not 12 volts, something less. While it is connected, it may be 11.2 volt, something less than 12 volt. Why did that happen? Why did that happen? Because some of the voltage of this EMF will be dropped when the current flows through this internal resistance. So what comes outside, we call it terminal voltage, will be less than this 12 volt. What comes and appear across this external resistance is called the terminal voltage, and it will be less than, so if I put it delta V, it will be less than the EMF of the battery. Unfortunately, we don't want that to happen. We want everything to come out, but because of the internal resistance, it will have reduced. So you need to know these things, okay? Internal resistance, battery has an internal resistance. Yeah. Yeah. Yeah, well, I mean, charging the battery is something else. I mean, I don't see the relevance here to talk about it. Yeah, 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 yeah. Um, well, I have to admit, I don't know the technical detail, and also it is outside. I understand the question, yeah, but I don't see the relevance here. So I really don't want to go in there. Okay. Also, I don't know the technical details, so I cannot tell with authority. Okay. So let's skip that. Okay. All right. So it has no relevance to what I'm teaching now. It will drag me back. We need to so concentrate on the basic stuff. Then we can talk about it later. Okay. Sorry about that. Okay. Right now, see, the battery before the whole thing is just the battery, right? Now I know this battery consists of its own resistance, which is called the internal resistance. So I'm going to replace this by this one to show that this battery has an EMF of E and it has got an internal resistance, small r. We use the small r for the internal resistance. So the potential that appears to this external resistance, the VAB, or if I call it delta V, will not be E, it will be E, the EMF, subtract how much of the potential is dropped across this, which will be I into R by Ohm's law. So this delta V is the terminal voltage, and that only the terminal voltage appear across this resistance. So you can see the terminal voltage is equal to I into capital R. Capital R for the outside resistance, we call it the load resistance. So when you say load resistance, that is the external to the battery. Whatever the resistances you have external to the battery is called the load resistance. The internal resistance is the resistance that is inside the battery. So if you put delta V is equal to IR, you get this. This is the, you can say the EMF has to supply the current not only to the external resistance, it should also supply currents to the internal resistance. So E is equal to the Ohm's law, I multiplied by the total resistance. The total resistance will be outside resistance plus the internal resistance. Right. This, suppose I go back to the, if I put a switch here and do not close the circuit, so there'll be no current, right? In that case, there'll be no current because I kept this open, no connection now. So therefore, there is no circuit, the current will not flow. When the current is not flowing, if I measure the potential difference across the battery, it will show E. Okay, because there is no current flowing, right? So this will be zero. Therefore, delta O, the terminal voltage will be equal to the EMF when there is no current flowing. But if the current flows, the terminal voltage will be less than the EMF. So for that reason, we also call this terminal voltage as the open circuit voltage, right? So if the battery is not connected to the circuit by opening the switch, then you measure the voltage across the battery, it will be the same as the EMF of the battery. But the moment you connect it and then measure, it will have a reduced value. And the external resistance is called the load resistance. Okay, so you can see the current that comes out will depend not only on the load resistance, it will also depend on the internal resistance. Okay, what happens usually, the load resistance will be high value compared to the internal resistance of the battery. This may be like 10 mega ohms or something, mega, okay? This can be just few ohms, maybe 10 ohms or 100 ohms, few ohms. So usually, I mean, you can ignore the internal resistance because of this reason. So that's what we assume, because whenever I put a battery, you can take it has no internal resistance. Now, I go back to the equation we had. Let me write it again here. We had this equation, okay, I R plus R. So that can be written like that. So we say the EMF will be equal to the Ohm's law, I into the resistance. We have two resistors, not just one resistance. Now, if I multiply this equation by I, both sides, this become IE, this become I squared R, and this become I squared small r. Now look at this equation. This is the power. This is the power from the battery, I epsilon, because we learned this power. Power is I into delta V. Delta V now from the battery, it will be E. So this is the power that is taken from the battery. And this is the power again. See, we had three equations, if you remember, for the power. It can be either given as I delta V or I squared R or I delta V squared over R. So this is the power that is spent or used, consumed by the resistance, the big resistance R, and this is the power that is being consumed by the internal resistance R. So the whatever the batteries give out, it will be shared by the load resistance as well as the internal resistance. So if this is true, we can say, okay, most of the power from the battery is going to the load resistance because the small r is small.